Hello. After the introductory session, we are now ready to work on the principles of structural analysis in earthquake engineering. We know the main concepts and terms used by the Eurocodes, and these apply to the Eurocode that refers to earthquake-resistant design. So we will make use of a combined knowledge of the workings and the wording used in the Eurocodes, together with theory principles from structural dynamics. Borrowing now the concept from material-specific design, as we have seen it in other modules based on the Eurocodes, the principle of the earthquake-resistant design consists of balancing the seismic capacity of structures with the seismic demand imposed by the earthquakes. So that is expressed by the inequality seismic capacity greater than or marginally equal to seismic demand. But how is seismic capacity and seismic demand defined? Seismic capacity of a given structure is a function of its structural elements, so it depends on the material and dimensions, of the typology of the structure, the foundation system, whether we are talking, for example, about shallow or deep foundations, and the soil conditions. The seismic demand of a given structure is a function of the magnitude of the earthquake, the soil conditions where our project is based, the module parameters, like the frequency, the damping, and the mode shape for our construction, and the foundation flexibility. As you know, and as we have discussed before, the primary intent of all seismic code provisions is to protect the life safety of building occupants and the general public through the prevention of structural collapse from a natural event such as an earthquake. This goal encompasses some objectives. We start from the small or moderate earthquakes, for which the target is to control the severity of the damage. Another goal, one step upwards, is to resist a minor level of ground motion without damage. The third one would be to resist a moderate level of ground motion without structural damage or only some non-structural damage. And finally, when we have a major event, our structures need to resist a major level of ground motion, having an intensity equal to the strongest either experienced or forecast for the building site, without collapse, but possibly with some structural as well as non-structural damage. In accomplishing these ends through codes, many variables involved in seismic design must be taken into consideration, such as the variability in ground motion, the soil type, the dynamic characteristics, material strength properties, quality assurance, and construction practices. If we want to become more specific for the seismic capacity of a structure, we need to try answering the question, what affects building performance damage? The structural components in a building include the foundation, the framing system, walls, connections, and roof and floor slabs. So the typology of the building system is crucial in the determination of its seismic capacity. Frame types include concrete, steel, and braced steel. The engineering profession had progressed fairly slowly until the early 1980s from the basic framing concepts that were first evolved in the early 1900s. When the concerns about seismic performance and energy dissipation became paramount, researchers and design engineers investigated mechanisms and configurations to supplement the basic rectangular grid framing in use for over 100 years. And let's see now some examples, starting from these pictures and sketches in this slide. Steel structures are considered the most seismic resistant, allowing smaller member sizes compared to reinforced concrete. But now, and after the experience of the Northridge earthquake in Southern California, steel structures have progressed from a simple steel frame braced laterally by unreinforced masonry, for example, to complete moment frames with full lateral load resistance. Trying to respond to the same problem, to the same question, what affects building performance and damage, we are going now to see some examples referring to walls. And we know that walls can be concrete, unreinforced masonry, infill and non-infill, reinforced masonry, or wood studs. Reinforced concrete, as you can see this building in the pictures, was used to be the general answer for all types of construction, small, medium, or large. Reinforced concrete framing became particularly popular at the beginning of the 20th century. Soon after bare concrete frames were developed, they were infilled with concrete shear walls for lateral stability. Not all of these buildings were well conceived structurally, and because of the ease of adding or deleting walls and openings, torsional problems became common. Current design approaches promote the benefits of confined concrete columns and ductile concrete frames, or dual systems of ductile concrete moment frames coupled with confined concrete shear walls. Among traditional structural materials, the most efficient one in terms of seismic resistance, specifically for low-rise buildings, is timber. Timber framing dates back thousands of years and has been used where timber was in good supply and building stone was not. If properly engineered, it guarantees survivability because of its lightweight as well as its flexibility. So we can be talking about rigid plywood shear walls or wood structural panel diaphragms with lateral bracing or tying components that guarantee connections from roof to foundation. Where the problems start is where, for example, we have large openings that greatly reduce the area of walls available to resist lateral and gravity forces, or significant irregularities in plan that introduce large eccentricities that lead to significant torsional loading. Another example here of wood frame construction with potentially problematic response to earthquakes is this case where the house is supported on cripple walls, and when the earthquake motion moves the foundation excessively, then the house rocks on the cripple wall and eventually falls when the wall collapses. More than other categories, timber buildings should be carefully designed and constructed, and with appropriate detailing and quality assurance in construction, they still present benefits, especially with reference to the sustainable building practices. The devastating Long Beach earthquake in 1933 revealed that masonry construction was dangerously seismically inadequate. This, of course, is more pronounced for pre-code masonry structures. In modern construction, we are talking exclusively about reinforced masonry. To achieve ductile behavior in masonry, it is necessary that the shear strength of the wall be greater than the tensile strength of the reinforcement, so that the wall does not fail in shear first, and to ensure a kind of bending failure by yielding of reinforcement. Moving away from the role of materials and structural typologies, it's worth noting the role of the general configuration of the building and the layout of its structural elements. A soft story building is a multi-story building in which one or more floors have windows, wide doors, large unobstructed commercial spaces, or other openings in places where a shear wall would normally be required for stability as a matter of earthquake engineering design. So we can see here examples of a partial soft story collapse due to inadequate shear strength at the ground level to the left from the 1989 Loma Prieta earthquake. And bringing this introduction and this route of thinking to an end, last but not least, we shouldn't underestimate the importance of the effect of non-structural elements to the building performance and damage, as well as to the risk for loss of human lives. Light fittings, cupboards, shelves, hanging ceiling parts can all modify the seismic hazard, most of the times unexpectedly. That is why detailing of installation and maintenance procedures, as well as compliance with product standards, are of paramount importance. We have understood from what was covered so far that earthquake design philosophy consists of the mitigation of the seismic risk. And there is a range of physical and socio-economic consequences that should be taken into account when the acceptable consequences are being decided, the acceptable earthquake risk for a certain construction. The seismic risk can be defined as the possibility of losses due to the effects of future earthquakes. Quantifying the costs of an earthquake is difficult, and of course, the most important losses are death and injury to human beings, and then we come to damage to the built and natural environments. Loss figures given for historical earthquakes are usually estimates based on aggregates of approximate information. In only a few cases have detailed studies been made to collect the actual costs incurred by all of the many people, businesses, and stakeholders affected by the earthquake, and to compile an overall assessment once the repairs and reconstruction costs are known. For now, we will just focus to some simple examples describing human losses and economic losses, as well as social losses that could be categorized under the term intangible losses. Intangible losses include also the human misery and the deprivation caused by the earthquake and its effects on morale and confidence. Earthquakes destroy also historical heritage and culture that contribute to the quality of our lives and our identity as a community. Earthquakes also disrupt communication networks, disrupt social activities, which means that people lose contact with friends, customers, and business suppliers. Based on relevant literature, from 1900 to 1999, earthquakes caused damage estimated to be worth more than $1 trillion at modern values. This represents the loss estimates from the historical repair costs of each of the 1,248 destructive earthquakes recorded around the world during that century, and adjusted to the value of money nowadays. So if resources were unlimited, seismic protection would be achieved by simply providing as much earthquake resistance as possible to a structure, almost limiting the seismic risk. But this is not the case. In practice, earthquake-resistant design seeks to balance the seismic resistance against expected levels of seismic hazard and acceptable damage. Obviously, some facilities demand greater earthquake resistance than others because of their greater social and financial significance. It is important to determine in the design brief not only the more obvious intrinsic value of the structure, its contents and function, or any special parts of it, but also the survival value placed upon it by the owner. We need also to keep in mind that the consequences of damage to structures housing intrinsically dangerous goods or processes is another category of consideration and concerns the potential hazards of fire, explosion, toxicity, or pollution represented by installations such as liquid petroleum gas storage facilities or nuclear power or nuclear weapon plants. So these types of consequences often become difficult to consider objectively as strong emotions are provoked by the thought of them. A good example is the following. Acknowledging the general public concern about the integrity of nuclear power plants, the authorities in the UK decided in the 1970s that future plants should be designed against earthquakes, although our country is of low seismicity and this kind of design is not generally required. The seismic risk is determined by the seismic hazard, which is estimated by the seismologists and refers to potentially damaging effects induced by earthquakes at a particular location, which may include the overall effects caused by an earthquake, such as surface rupture, tsunami, liquefaction, and landslides, as well as earthquake-induced ground acceleration. Exposure, which is controlled by planners and investors, and refers to the people, buildings, and infrastructures located in an earthquake-prone area. The exposure to the seismic risk can be reduced by planners and investors by relocation of the new infrastructure. And finally, vulnerability, which is controlled and estimated by engineers, as we have stated before, and can be defined as the expected degree of damage under different level of seismic demands produced by earthquakes. And this vulnerability can be controlled by engineering design, which will be our focus in this module. As explained earlier, the assessment of the seismic hazard due to the future earthquakes involves the seismicity model, which should prescribe the location, the size, and frequency of future earthquake in the region, the ground motion module, giving the prediction of expected levels of shaking at a given site, and the expected level of shaking experienced by the structure, expressed by the response spectra, the function of soil conditions, and model parameters of the structure, These three models summarize the requirements of the seismic design that we have briefly outlined earlier. And we will now examine them one by one to understand what exactly we mean and how all these contribute to modern seismic design. With our efforts so far to determine the seismic hazard being focused on the seismicity model, we will now move towards the ground motion model and how we can estimate features such as the peak ground acceleration depending on the earthquake magnitude and the distance from the epicenter to the location of a specific structure. To do that, we are going to briefly review some basic terms that we know from physics and structural dynamics. What do the physics tell us about the magnitude of the forces that different types of buildings feel during an earthquake? We have to use first principles such as the Newton's second law of motion, linking the exerted force to the acceleration experienced by a mass. The force induced by an acceleration is, as we know, proportional to the mass. This is known as D'Alembert's principle, and based on the sketch here, you can see that in essence, it means that any system of forces is in equilibrium if impressed forces are added to the inertial forces. We can transform an accelerating rigid body into an equivalent static system by adding the so-called inertial force, and this inertial force must act through the center of the mass. It should be proportional to its acceleration and opposing it. We will now go through a brief account of the basics of dynamic behavior of structures so that we will be able at the right point to understand the representation of earthquake ground motion by response spectra. Some basic definitions now. Frequency is the number of complete cycles of vibration per second, and the period is the inverse of frequency, which is the time needed to complete one full cycle of vibration. The structural dynamics problem can be idealized as a system with a lumped mass and a massless supporting structure. We are interested in understanding the vibration of these structures when subjected to a lateral or horizontal force at the top or horizontal ground motion due to an earthquake. As you can see in this sketch, these simple structures are idealized as a concentrated mass M supported by a massless structure with stiffness K in the lateral direction. From the basic formula linking the period to the mass and the stiffness for these kind of systems, we can easily see that the smaller the stiffness, the larger the building's period for the same mass. Similarly, the period increases proportionally to the mass, meaning a bigger mass leads to an increase in the building's period. We can see here a single degree of freedom system in the form of a frame structure that consists of a mass M concentrated at the roof level, a massless frame that provides stiffness to the system, and a viscous damper, also known as a dashpot, that dissipates vibrational energy of the system. The beam and columns are assumed to be inextensible axially. This system may be considered as an idealization of a one-story structure. Each structural member, beams, columns, or walls of the actual structure contributes to the inertial, elastic, and energy dissipation properties of the structure. In the idealized system, however, Each of these properties is concentrated in three separate pure components: the mass component, the stiffness component, and the damping component. As we can see from the sketch, considering this system, there is no dynamic excitation other than the force F, which is given here as a function of time t, and is externally applied along the degree of freedom u, with the relationship between the two, as depicted here in the graphs, being associated with deformations in the structure during the oscillatory motion. In actual structures, many mechanisms contribute to the energy dissipation. In a vibrating building, these include friction at steel connections, opening and closing of microcracks in concrete, and friction between the structure itself and non-structural elements, such as partition walls. It is impossible to identify or describe mathematically each of these energy dissipating mechanisms in an actual building. That results to the damping being in actual structures represented in a highly idealized manner. It can be given satisfactorily by a linear viscous damper or dashboard, as you can see in this more advanced equivalent frame. The damping coefficient is selected so that the vibrational energy dissipates is equivalent to the energy dissipated in all the damping mechanisms combined present in the actual structure. So have a look now at this idealized one-story frame as introduced earlier, that is subjected to an externally applied dynamic force in the direction of the degree of freedom u. Both the force and the resulting displacement of the mass vary with time. So we can derive the differential equation governing the displacement u as a function of the time by applying Newton's second law of motion. Alternatively, having been trained to think in terms of equilibrium of forces, we as structural engineers may find D'Alembert's principle of dynamic equilibrium more appealing. We can then create the free body diagram of this structure at time t, with the mass replaced by its inertia force. In either way, setting the sum of all the forces equal to 0 gives us the derivation of the equation of motion. We are now at a point where we have formulated the governing equation for the idealized one-story frame based on the action of the external force F, and we are describing now the state of the system by introducing terms linked to the displacement u, the velocity, which is the first derivative of the displacement, and the acceleration, that is the second derivative of the displacement. Now you can visualize the system as a combination of three pure components: the stiffness component, the damping component, and the mass component. As mentioned earlier, the damping in actual structures is usually represented in a highly idealized manner. We have been using a linear viscous damper under the concept of an equivalent viscous damping approach that encompasses the energy dissipation in all damping mechanisms. As discussed earlier, the damping force, Fd, is related to the velocity, which is the first derivative of the displacement, across the linear viscous damper by a formulation that calculates the product of the constant c, which is the viscous damping coefficient, with the velocity. The equivalent viscous damper is intended to model the energy dissipation at deformation amplitudes within the linear elastic limit of the overall structure. If we want now to create a graphical representation and interpretation of the energy dissipated in viscous damping, we will derive an equation relating the damping force to the displacement. The damping force versus displacement curve forms a loop known as a hysteresis loop. The energy dissipated by damping is the area enclosed by the ellipse. Finally, and before starting our specific discussion for the seismic actions on structures, let's see some basic concepts of energy absorption and dissipation. For a linear system, the relationship between the lateral force and resulting deformation U is linear, as you can see on the top left sketch. This linear relationship implies that the force is a single-valued function of U through K, which is the lateral stiffness of the system. We use the term linearly elastic system, for which the energy absorbed during loading is recovered through the reversibility of phenomena after unloading. Increasing the load further, or just being at larger amplitude of deformation that makes more sense under a seismic excitation, we are past the yielding point, which means that we have now the dissipation of energy that is predicted by the red area under our top right sketch. In this simplistic representation of phenomena, while unloading, part of the energy is recovered as the unloading path follows a route parallel to the first linear elastic loading one, and the recovered energy is expressed through the area under the yellow triangle, whereas in such a behavior, the energy dissipated is the sum of the light blue and the red areas at the final graph. In the general case, the force deformation relation for a structural member undergoing cyclic deformations expected during earthquakes is path dependent, which means that it depends on whether the deformation is increasing or decreasing. So far, we have introduced the single degree of freedom system by idealizing a one-story structure. We are now going to see how this and the basic principles of physics that we just reminded ourselves are related to ground motion and seismic action. The action induced by an earthquake, the seismic demand, can be estimated from the acceleration induced by the ground motion. And going back and thinking about how D'Alembert's principle is applied, the seismic force acting on a structure can be represented by an inertia force. The ground acceleration can be estimated from the time history of the earthquake. So AG is now our ground acceleration, which multiplied by the mass of the structure, or the structural member, gives us the corresponding inertia force. So you can see how a time history acceleration would look like here for the strong motion for the 1940 El Centro earthquake, the north-south component, where we have the recording of the acceleration as a function of time. Measurement of vibration is of great interest in many aspects of structural engineering. For example, measurement of ground shaking during an earthquake provides basic data for earthquake engineering, and records of the resulting motions of a structure provide insight into how structures respond during earthquakes. Most of the developments in the field of earthquake design were related to the acquisition of high-quality recordings of strong ground motions using seismographs and accelerographs. Although measuring instruments are highly developed and intricate, the basic element of these instruments is some form of a transducer. In its simplest form, it is a transducer, like a mass spring damper system, mounted inside a rigid frame that is attached to the surface whose motion is to be measured. The motion to be measured generally varies arbitrarily with time and may include many harmonic components covering a wide range of frequencies. There are closed-form solutions giving the displacement of the instrument mass relative to the moving frame, and then computations can be carried out by discrete Fourier transform procedures to obtain the actual ground acceleration. Considering D'Alembert's principle, the maximum seismic action is given as a function of the peak ground acceleration obtained by the time history in terms of accelerations multiplied by the mass of the structure. Just note that we should always be working with compatible units, which would indicatively be here meters per squared seconds for the acceleration and newtons for the forces. To manage earthquake risk, it is essential to know the size of the risk and the amount by which the risk is reduced by taking some particular action or set of actions. The first concepts for structural design in seismic areas were developed from experience gained in catastrophic events such as the San Francisco earthquake in 1906 and the Messina earthquake in 1908. At the very beginning, there were no experimental data. The method just consisted of designing structures to resist uniform accelerations of the order of 0.1 g. After the Long Beach earthquake in 1933, recorded time histories showed that the ground accelerations could reach values as high as 0.5 g. And although written descriptions of earthquakes date back as far as 780 BC, the first accurate measurements of distracted ground motions were achieved during that particular earthquake in 1933. We will now discuss the principle underlying the design of vibration measuring instruments so that the measured relative displacement provides the desired support motion, either in the form of acceleration or displacement. The importance of such instrumentation is stated by the National Research Council Committee on Earthquake Engineering Research that states the recording of strong ground motion provides the basic data for earthquake engineering. Without the knowledge of the ground shaking generated by earthquakes, it is not possible to assess hazards rationally or to develop appropriate methods of seismic design. Various instruments are available for ground motion measurements, and we are going to discuss two categories of those. The seismographs, which due to their high sensitivity are used to measure relatively weak ground motion, and the accelerographs, which they currently come in the two main forms of analog or digital. The simplest type of seismograph can be illustrated, as we have discussed earlier, by a mass damper single degree of freedom system. A rotating drum is connected to the seismograph housing with a stylus attached to the mass. The mass is connected to the housing by a spring and dashpot that are parallel with each other. The housing is connected to the ground, and since the spring and dashpot are not rigid, the motion of the mass and the stylus will not be identical to the motion of the ground during an earthquake. The relative movement of the mass and ground will be the trace made by the stylus. I remind you that a single degree of freedom system is one whose deformation can be completely defined by a single displacement. The seismograph can be studied as such a mass spring damper single degree of freedom system, an oscillator whose response to the shaking is given by the equation of motion. Our single degree of freedom system is subjected to a time-varying external force which causes a displacement u. The movement of the mass generates restoring forces in the spring and damper, as shown in the free body diagram on the right. By Newton's second law, the resultant force is equal to the mass multiplied by the acceleration. And you can see here each dot represents one differentiation with respect to time, so that we have here the velocity and here the acceleration. So this is known, as we have said before, as the equation of motion of the system. An alternative way of coming to the same result is to treat the term m times acceleration as an additional internal force, which is the inertia force, that acts on the mass in the opposite direction to the acceleration. The equation of motion is then an expression of dynamic equilibrium between the internal and external forces. The inertia force plus the damping force plus the stiffness force altogether equal to the external force. U is the seismograph trace displacement, the relative displacement between the seismograph and the ground. UG is the ground displacement, and let's let the ground displacement be a simple harmonic at a circular frequency omega, which is the forcing frequency, and see how this equation gets transformed. As explained in the previous slide, we can identify three types of displacement in our effort to express mathematically the behavior of a mass spring dashpot system under a harmonic loading. We have the ground displacement, UG, the relative displacement, U, and the total displacement, U total, which is equal to the sum of UG and U. In an earthquake, there is no force applied directly to the structure. Instead, the ground beneath is subjected to a predominantly horizontal time-varying motion, as you can see from the sketch. Note that the stiffness and damping forces are proportional to the relative motion between the mass and the ground, while the inertia force is proportional to the absolute acceleration experienced by the mass. Based on this concept, this is what we get in the absence of any external forces by applying Newton's second law. We can now rewrite the equation of motion as a function of the relative displacement between the mass and the ground. So, a seismic ground motion results in a similar equation of motion to an applied force, but in terms of motion relative to the ground and with the forcing function proportional to the ground acceleration. We will look now at solution to these equations. First of all, supposing that the ground motion varies sinusoidally with time at a circular frequency omega, with the corresponding period being t equal to 2 times p over omega. Of course, a real earthquake ground motion is more complex, but this simplification serves to illustrate the main characteristics of the response. After combining the harmonic loading with the equation of motion and dividing by the mass m, using the relationship for damping ratio and natural frequency, the equation of motion can be rewritten as a function of the damping ratio, the natural frequency, and the harmonic loading. The complete solution of the equation of motion comprises two parts. First, the solution for the viscously damped free vibration, which is called the complementary solution. This is also referred to as transient solution of the damped system. And the particular solution, that is also referred to as steady-state solution. As we know from maths with applications to structural dynamics, by setting the external force equal to 0, we get the differential equation governing the free vibration of the single degree of freedom systems with damping. And this is what we call the equivalent homogeneous equation. The solution to this equation, subject to the initial conditions for systems with underdamping, meaning a damping coefficient less than the critical damping coefficient, is called the complementary solution, that is a function of omega d, which is the natural frequency of the damped vibration. Similarly, the natural period of damped vibration, Td, is related to the natural period T0 through C, which is the damping ratio. The equation of the complementary solution is plotted in this graph below, which shows the free vibration response of a single degree of freedom system with a damping ratio of 5%. Included for comparison is the free vibration response of the same system but without damping. Free vibration of both systems is initiated by the same initial displacement and velocity, and hence both displacement time plots start at t equals to 0 with the same ordinate and slope. The displacement amplitude of the undamped system is the same in all vibration cycles, but the damped system oscillates with amplitude decreasing with every cycle of vibration. Damping has the effect of lowering the natural frequency from omega 0 to omega d and lengthening the natural period from T0 to Td. These effects are negligible for damping ratios below 20%, a range that includes most structures, as you can see here in this graph. For most structures, the damped properties omega d and Td are approximately equal to the undamped properties omega 0 and T0 respectively. The more important effect of damping is on the rate at which free vibration decays. It is worth discussing the relation between the ratio of two successive peaks of damped free vibration and the damping ratio. The ratio of the displacement at time t to its value a full vibration period Td later is independent of t. We can plot the successive peaks, maxima of displacement, that are separated by period Td, and then formulate the ratio ui over ui plus 1. The natural logarithm of this ratio is called the logarithmic decrement, and we denote that by delta. If the damping ratio is small, then we get an approximate equation where the logarithmic decrement is a linear function of the damping ratio. Coming now back again to the full solution of the equation of motion, and having so far discussed about the limitations of the complementary solution, we are now moving to the particular solution that is also known as the steady-state solution and depends on the external excitation. I remind you that we have considered our single degree of freedom system being subjected to a harmonic force. The differential equation is to be solved subject to the initial conditions of displacement and velocity being equal to 0. The general form of the particular solution is a function of constants C3 and C4 that can be expressed as a function of the frequency ratio β, that is the ratio between the forcing frequency and the natural frequency. The full solution contains two distinct vibration components, the forced vibration for excitation frequency omega, the solution of which you can see here as UP, and the free vibration that we discussed previously. So, to summarize what we have done so far, we have provided the solution to the differential equation governing the response of single degree of freedom systems to the harmonic force defined earlier. So this solution comprises the complementary and the particular solution, with the complete solution of the equation of motion containing two distinct vibration components, one coming from the forced vibration. We can see that through the terms that contain omega, and the free vibration through the terms that contain the natural frequency omega 0. We can see the full solution plotted in this graph, where the total response is shown by the solid line and the forced response is shown by the dashed line. The difference between the two is the free response, which decays exponentially with time at a rate depending on the ratio omega over omega 0 and the damping ratio. Eventually, the free response becomes negligible. That's why we call it transient response. After a while, essentially the forced response remains, which we call steady-state response, and this will be our main interest from now on, although it should be recognized that the largest deformation peak may occur before the system has reached the steady state. As explained from the previous graph, the forced response essentially remains, so we are particularly interested in rewriting and working with this, just the steady-state harmonic. The particular solution can be rewritten in a simplified form, expressed as a function of the response amplitude ρ and the phase angle theta. The ratio P0 over K is the static displacement that controls the amplitude of the static deformation. The maximum value of the static deformation, P0 over K, may be interpreted as the static deformation due to the amplitude P0 of the force. Having solved and commented on the solutions of the equation of motion, and having defined the maximum amplitude of the response as well as the static displacement as a function of P0, we are now defining the dynamic amplification factor D that measures the degree of amplification of the dynamic response with respect to the static response as induced by the same load applied statically. The dynamic amplification factor is an important parameter for the identification of resonance phenomena. A resonant frequency is defined as the forcing frequency at which the largest response amplitude occurs. Note that at the resonance, beta equals to 1, where the forcing frequency and the natural frequency are identical, the amplification depends on the damping. If we are now to put this mathematical background into a more visualized context, we are plotting the dynamic response factor as a function of the ratio omega, the forcing frequency, over omega natural. So we have defined that as beta. So just observe what happens when we have no damping and the dynamic amplification factor approaches peak values for beta equals to 1, while gets towards 0 as beta moves towards infinite values. As you can see, for all damping ratio values, the response factor is unity at beta equals to 0. We will now examine the role of damping in the rate at which steady-state response is attained and in limiting the magnitude of this response when the forcing frequency is the same as the natural frequency. So for omega equals to omega n, the natural frequency, the deformation response factor is dimensionless and defines the amplitude that is followed by the displacement as a response quantity. The response ratio is plotted here for damped and undamped systems, and that shows that damping lowers each peak and limits the response to the bounded value. As we can see, the deformation varies with time as a cosine function, with its amplitude increasing with the time according to the envelope function shown by the dashed lines. Obviously, the amplitude of the steady-state deformation of a system to a harmonic force with omega equal to the omega frequency of the natural system and the rate at which steady state is attained is strongly influenced by damping. We will now apply the knowledge that we got in general terms from structural dynamics to the response of a single degree of freedom system to harmonic ground motion. This is of particular interest for the determination of the response characteristics of seismographs to harmonic-based displacement. It is desired to design the transducer so that the relative displacement U as a function of t measures the support displacement Ug as a function of t. For ground motion frequencies well above the natural frequency of the seismograph, meaning we are at large values of beta, the trace amplitude U is equal to the ground motion Ug. The lowest frequency for which this equality holds depends on the damping ratio. Because the frequency response is flat at damping of 50 to 60%, single degree of freedom seismographs are generally designed with damping ratio in this range. This basic concept is clear, but to be achieved, we would need a transducer spring so flexible, or the transducer mass so large, or both, that the mass stays still while the support beneath it moves. Such an instrument is unwieldy because of the heavy mass and soft spring, and because it must accommodate the anticipated support displacement which may be as large as around 1 meter during the earthquakes. The recorded u as a function of t is the base acceleration modified by a factor dependent on the ratio of the dynamic response factor as expressed in terms of displacements over the natural frequency squared. And that is recorded with a time lag of the phase angle over the forcing frequency. The object of the instrument design is to make the dynamic response factor and the ratio of the phase angle over the forcing frequency as independent of excitation frequency as possible, because then each harmonic component of acceleration will be recorded with the same modifying factor and the same time lag. We can see here that the trace of the seismograph is proportional to the ground acceleration amplitude for frequencies well below the natural frequency of the seismograph, meaning low values of β. That means that most seismographs have natural frequencies of about 25 Hz with damping ratio near 60% by choice, with a desirable flat response at frequencies up to 13 around Hz. Most of the accelerographs currently in use consist of accelerometers. Accelerometers are electronic transducers that produce an output voltage proportional to acceleration. They are commonly classified into servo or force balance accelerometers that have a suspended mass to which the displacement transducer is attached, and as a consequence of the relative displacement between the housing and the mass, a restoring force is generated that pushes the mass back towards its equilibrium position. The restoring force is proportional to the acceleration. A second class of accelerometers comprises the piezoelectric accelerometers, for which the mass is attached to a piezoelectric material, usually quartz or ferroelectric ceramics. The piezoelectric material acts as a spring. When the mass is accelerated, the inertial force of the mass strains the piezoelectric material, which develops an electrical charge that can be measured. Piezoelectric accelerometers have negligible damping and high resonance frequency, so they are particularly useful for high-frequency measurements. In earthquakes, the motion of any particle of the ground follows in general a complex three-dimensional path having rapidly changing accelerations, velocities, and displacements, and a broad band of frequency content. Strong ground motion is measured by a large amplitude type of seismograph called an accelerograph, as we have seen before, in the form of an accelerogram, which is an acceleration history, typically of the form as you can see in this picture, while the velocity and displacement histories are obtained after the earthquake by integration of the acceleration record. That summarizes our concept that the most common way of describing a ground motion is with a time history, expressed either in the form of acceleration or velocity or displacement. Not only is earthquake ground motion complex and irregular, but no two earthquakes are the same. In an attempt to obtain an adequate understanding of earthquake ground motion, a number of parameters have been used to characterize it, and some of the most important ones comprise the peak ground acceleration and the root mean square acceleration. As we just said, a strong ground motion can not only be expressed in terms of an accelerogram through the peak ground acceleration and other characteristics of the time history recorded by the accelerogram, but also through velocity histories that are similarly characterized by the peak ground velocity and the root mean square velocity. And last case here, obtained by double integration of the acceleration record, we can get the displacement history characterized by the peak ground displacement and the root mean square displacement. All these characteristic factors, PGA, PGV, PGD, and the root mean square values of the acceleration, the velocity, and the displacement are measured from the respective ground motion records that, as we said, are often referred to as time histories. The frequency of vibration associated with the amplitudes of motion is, of course, an intrinsic characteristic of earthquake ground motion, and frequency content is commonly studied in spectral form, as we are going to see in the next sections. For now, we are focusing on the study of these time histories, as we explained earlier, starting from an acceleration history and then getting the velocity and displacement histories after the earthquake by integration of the acceleration record. We observe that the acceleration time history has a significantly shorter period or higher frequency than the corresponding velocity and displacement records, while the amplitude of the acceleration record is omega squared times greater than that of the displacement. The frequency content of ground motions is a function of a number of phenomena such as the source mechanism, the depth, the distance from the source, the nature of the travel path and site soil, and the magnitude of the event. In any case, we can see that the acceleration record intensifies high-frequency components. Now that we have a good understanding of the different time history recordings that we can work with based on earthquake excitations, it is worth thinking about how these are related to the actual response of structures. Think about them as the external excitation to your single degree of freedom structure. We have talked about and solved the equation of motion, and by observing the solution, we found that for a given ground acceleration, the deformation response of the structure depends only on the natural frequency omega 0 of the structure and its damping ratio. Any two systems having the same values of natural frequency and damping will have the same deformation response, even though one system might be heavier or stiffer than the other. Let's try to link again what we already know from the mathematical approach to the solution of the equation of motion together with what we just explained regarding recording and using actual excitations from seismic events. Of great interest in structural engineering is the deformation of the system, or the displacement of the mass relative to the moving ground, to which the internal forces are linearly related. Why are we interested in the internal forces? These are the bending and shear forces in the structural element that will actually determine its design. Knowing the total displacement UT of the mass would be useful in providing enough separation between adjacent buildings to prevent their pounding against each other during an earthquake. Pounding is the cause of damage to several buildings during almost every earthquake. Similarly, the total acceleration of the mass would be needed if the structure is supporting sensitive equipment and the motion imparted to the equipment is to be determined. For a given ground motion, the deformation response U as a function of t of a single degree of freedom system depends only on the natural vibration period of the system and its damping ratio. In this figure here, you can see the deformation response of three different systems due to the L central ground acceleration. The damping ratio is 2%, the same for all three systems, so that the only differences in their natural periods are those that are responsible for the large differences in the deformation responses. It is seen that the time required for a single degree of freedom system to complete a cycle of vibration when subjected to this earthquake ground motion is very close to the natural period of the system. The peak deformation is also noted in each case. Observe that among these three systems, the longer the vibration period, the greater the peak deformation that is recorded. As will be seen in the following, this trend is neither perfect nor valid over the entire range of periods. In this figure here, we can see the deformation response of three systems to the same ground motion. The vibration period is the same for the three systems, so that the differences in their deformation responses are associated with their damping. We observe the expected trend that systems with more damping respond less than lightly damped systems. Because the natural period of the three systems is the same, their responses display a similarity in the time required to complete a vibration cycle and in the times the maxima and minima occur. In attempting to understand and then quantify seismic activity, we need to work with a framework of global tectonics so that we try to relate seismicity to quantifiable deformational features or to major geological structures. Earthquakes occur at irregular intervals in space, size, and time, and in order to quantify seismic hazard at any given site, it is necessary to identify the patterns in the spatial, size, and temporal distributions of seismic activity in the surrounding region. Let's consider the maximum horizontal acceleration values recorded in the San Francisco Bay, which was shaken by the 1989 Loma Prieta earthquake. And you can see here in this figure the peak values of accelerations recorded at many different locations during the Loma Prieta earthquake. You can see the epicenter located near the bottom of the figure. Observing the values given, we can see that the acceleration values are largest near the epicenter of the earthquake and tend to decrease with distance from the fault causing the earthquake. However, the accelerations recorded at similar distances may vary significantly because of several factors, especially local soil conditions. If you check the upper half of the figure, the area of soft soils along the Bay Coast had stronger acceleration. This implies, of course, that softer deposits amplified the earthquake motion. And to build upon our understanding regarding the response history of soil deposits, it is worth noting in this picture the effects from the 1985 Mexican earthquake, which was famous for heavy damages to the buildings in the Mexico City. It was located at 390 kilometers from the fault area, but still, the capital city suffered significant damages. Let's start with some thoughts. We know that ground acceleration varies with time in a highly regular manner. No matter how irregular, the ground motion is presumed to be known and independent of the structure response. This is equivalent to saying that the foundation soil is rigid, implying no soil structure interaction. Is that true? Is that the complete picture? If the structure were founded on very flexible soil, the motion of the structure and the resulting forces imposed on the underlying soil can modify the base motion. This might be the start of the explanation for this phenomenon. Today, it is believed that the locally strong ground motion was caused by the soft deposit of soil in Mexico City. The Mexico City basin used to be a big lake, which was buried both naturally and artificially. The natural period of the soil deposits were very similar to the predominant period of the earthquake, having as a consequence significant amplification of the motion. As you can see in the graph, at around 400 kilometers distance from the epicenter, where the city of Mexico is located, there is a sudden increase to the horizontal acceleration components, but as we said, is reasonably attributed to the resonance between the ground and the earthquake. And let's remember a bit what we were doing in terms of assessing the amplification factors for the simplest dynamic system, which we were considering being a single degree of freedom system consisting of a mass on a spring, which remains in the linear elastic range when vibrated. The dynamic characteristics of such a system are simply described by its natural period of vibration and its damping. And we had considered this structure being subjected to a harmonic base motion. What happened then? We had demonstrated the significance of the natural period or frequency of the structure by comparing with the large amplifications of the input motion at or near what we had called the resonance conditions. And this is what we are going to do now, again, considering our soil layers as our structure. Following the same concept, when the predominant frequency of the earthquake is close to the natural frequency of the soil deposit and or the structure, there is significant amplification effects. As we just said, we have resonance phenomena when we have the omega, the frequency of the earthquake, which frequency we're going to explain just now, being equal with the natural frequency of the soil deposit or the structure. The predominant frequency of the earthquake represents the frequency range over which the earthquake releases its maximum energy. This energy is associated with a ground motion and can be identified in the frequency domain because energy is proportional to the power spectral density. To get that, we need a fast Fourier transformation from the time domain to the frequency domain, where a graph expressing acceleration as a function of time is transformed for an earthquake's component to a graph linking the power spectral density to the frequency. To obtain a complete predictive model for the ground motion at a given site, it is necessary to describe fully the ground motion at the source and to describe the modifications to the ground motion as it propagates from source to site. The amplification of the ground motion is minimum for very stiff structures where the omega natural is very high, leading to a minimum close to zero beta. For this reason, it has become customary to identify the peak ground acceleration at the bedrock or outcrop. There is a range of problems involved in adequately representing seismic behavior in theoretical analysis, and many compromises have to be made. To obtain the maximum benefit from any method of seismic analysis, an understanding of the dynamic response characteristics of materials is essential. The presence of soil overlying bedrock modifies the excitation in a complex manner with conflicting effects dependent on dynamic characteristics of the soil layers and the strength of excitation. The effects of topographic irregularities and alluvial basin geometry on ground motions can be significant. In many earthquakes, the degree of damage to structures situated on soils has been reported as worse than that occurring on adjacent bedrock sites. And this is attributed to the fact that the ground motion generated at the source will be affected by modification in amplitude and frequency content as the seismic front propagates through soil deposits. The modifications to the incoming bedrock motions are dependent on several factors, such as the amplitude of shaking, the frequency of vibration, the properties of the soil, such as their modulus and damping, the geometry depth and stratification of the soils, as well as the water level and the possibility of liquefaction. It follows from what we have already said that it is essential to understand the dynamic properties of the soils as well as structures in order to predict their response. There is a great variety of possible geological and soil conditions at construction sites, which give rise to a variety of responses in earthquakes. Depending on the location where the ground motion is measured, it is possible to distinguish between the free surface motion, which is the motion at the surface of a soil deposit, the bedrock motion, which is the motion at the base of a soil deposit, and the rock outcropping motion, which refers to a location where bedrock is exposed at the ground surface. Based on what we said regarding amplification, it is reasonable to see why Eurocode 8 suggests that the seismic action should be specified from the peak ground acceleration at the bedrock or outcrop. How realistic is that with respect to ordinary structures that we are called to design as engineers? What kind of modifications do we need to take into account with respect to initial Eurocode provisions? Regardless of the sources available and the methods available for analyzing the basic response phenomena, it should be borne in mind that knowledge of the real dynamical characteristics of the underlying soils is always incomplete, and the sophistication of the analysis used should not exceed the quality of the available data. This is why in the next chapters, we will be putting our emphasis more on practical design procedures than towards research methods, and this is exactly what Eurocode 8 does. Thank you for your attention, and I will be very happy to help you with any questions you might have.